Welcome back to the channel and the last video of 2024 for me. Hope everybody's doing well. And at the end of the year, a lot of people like to look back throughout the year of what's been going on. I thought I'd look back a little bit further than this, back to what I believe around about 1963 with this little instrument from my collection. And this is a Thermocouple Potentiometer, and this is an old analogue instrument for sourcing and measuring millivolt signals from thermocouples. And we did some work with thermocouples with our three amigos over to the right here, our Mr. Signal, Fenersi and LB02. And I showed you how these units worked with thermocouples both in temperature measurements and in millivolt measurements as well. Now whilst this unit here doesn't have the full functionality of these modern digitised units, surprisingly enough, it does actually have a function that I couldn't find on any of these units, and I'll show you that when we start doing some testing with it. This instrument itself is a type P6 down at the bottom here and is made by Cropico. Cropico started out life back in 1952 as the Croydon Precision Instrument Company. I think it got shortened to Cropico quite quickly, and it actually remained as a family-owned business up until 2006 when it was sold into the Seawood Group. If you're a UK-based electrician, highly likely you'll have heard of Seawood. They have a huge range of test apparatus. Some of that they've developed themselves, some of it they've developed through acquiring other businesses. Nowadays, Cropico is just a brand name within Seawood, and you'll find its name on their micrometers, resistance standards and decade boxes. But it's no longer a company in its own right. However, back in the 50s, 60s and 70s when it was a company, it was highly successful in developing a lot of instrumentation for use in telecommunications and other industries, with the likes of equipment like this and decade boxes and other bridges. And in the 1990s it formed a business deal with another company in Norwich to move into more digital equipment away from their old analogue designs. Now this would have been in direct competition with instruments from Cambridge Instruments, and the information I have available to me from the old engineers that used to use these type of equipment is that this was really seen as a bit of a poor man's instrument in regard to Cambridge Instruments. Now that could be something to do with the prestige of Cambridge, university city, and all the engineering and academia that area is involved in comparison to Croydon, which is a borough down in the south of London and is actually the main town within that borough. It could also have something to do with the fact that this appears to be built into a cardboard box. If we look at the edges here, you can see, especially where it's come away, you can see the cardboard sandwiched in between these two layers, and especially down at the corner here where the hinges started to break, you can see the cardboard inside there. These two coverings, the inner one and the outer one, I believe are some sort of vinyl. I don't think they are leather. You do have Cropico labelling on the front here in gold leaf, and then you have underneath these 6 rubber feet screwed in through the case into the metal chassis of the instruments and hold the instruments in place. So when we have a look inside, we'll undo all of those to get a peek at what's going on in there. We do have a carry strap with it, and that is actually leather, but it is broken. We have to try and think of repairing that in some sympathetic manner, hopefully. But that's not uncommon for these instruments of this area, for the straps to get broken away. It is easily over 60 years old now, isn't it? So it's seen some action. Inside we have 2 instruments, and this is 2 separate instruments here. We have the measurement function and the sourcing function on this side. We do have a standard mercury thermometer here for measuring the cold junction temperature, and then we have a little instruction on the front here along with these discs that sit around here, and this is what you change the ranges and the type of function that you're measuring, along with one that's actually already installed on the set here. Now back in the day, whereas nowadays we are used to your K-type and J-type and whatever other type of thermocouples by letters. That didn't actually come out till around about 1982, I believe. I think it was the Instrument Society of America produced a standard that applied lettering to the types of thermocouples. Up until that point, they were known by their metals. So for this instrument here, we have chromal luminal, which is K-type, and we have 2 discs for that for different ranges. We also have a 13% rhodium platinum, and that is a type R, and it's just the 1 disc for that, because the other disc is a 10% rhodium platinum, and that is a type S. We also have copper constantan, which is a T-type. We just have the 1 disc for that because of the much shorter range for a T-type thermocouple. And we have the iron constantan, which is J-type, and again 2 discs for that to cover the wider range that has. And our final one is a millivolts range as well. So that's all those there. What we will do is we will have a juggle around and we'll set up a thermocouple and do some measurements. So we've set up, we're just waiting for our thermocouple to get to temperature. We're going for 110 degrees C, no specific reason, that's just what we can do. We'll just go through the operation of this test set. We are, as I said, we have the source function on here. We won't be using just at this moment in time, but the output is set on our 2 rheostats here, of course, and fine, and then we just switch it on and off using the 2 output jacks there into the instrument. On this side we have our measurement function. We have a null balance meter in the middle. We have our range set up. I've set this up for our K-type, 0 to 720 degrees C on this range. We're in 110, so that will be fine. And then we have calibration rheostat here that they called standardizing on this type of instrument, and we have our function selection here from off for standardizing, range 1 and range 2. Down at the bottom here we have our what's called our galv key, and we use this to test the setting that we've got, looking for the null balance on the meter there. So we are now at 109.9. We know we've got the right disc on, so the first thing we have to do is standardize the instrument. Now with standardizing, all I'm doing is calibrating this range measurement to the internal reference voltage within the instrument itself. Unfortunately, this switch has got a bit too old and it's not working very well. The instrument should be responding now, but as you can see, there's no movement there. So unfortunately, it's not operating quite as it should, but with it budged over a little bit, you can see we do get the needle to operate, and as I turn this rheostat up here, you can see deflection gets less and less. And what I'm looking for is no deflection whatsoever from the needle. If I go too far, then it goes the other way. That's pretty much no deflection there. So now we've done that, we can turn it to our selected range. They have actually coloured these dials, so this is red, so move to 0.1 there on the function switch, and we're ready to plug our thermocouple in, which just goes straight into the 2 jacks at the top here. Try and get the lead out of the way. And next thing we need to do is set the cold set junction temperature. Our thermometer on here, you probably won't be able to see too well, but that's reading 20 degrees C. So we loosen off the dial him round to 20 degrees C, which is somewhere near there. We are then ready to start testing. You see, we press the button in and you see we get deflection. So if we now move it, say, to 200 degrees C, we press the button again, it deflects the other way, it means we've gone too far. So now we need to start going back. You see deflection is less, so once you start getting small deflection in it, you've got 2 choices. You can then just make smaller movements if you like, or you can start walking the dial into the desired temperature where you get no movement, very little movement there. So we've got no movement there, we can carry on going back. 1, 2, little bits of movement there then. So we are no movement there, and what are we? Looks like it's on about 109. Unfortunately, somebody's put the camera in the way, so I can't see very well as we zoom in. Yeah, I think it's showing 109, so 1 degree out in comparison to what you can see on our dry well there, but the sensor is plus or minus 2 degrees C anyway on a K-type thermocouple. So what I will just show you is how this compares to our MR9270S here. We've got our common out and the 2 input terminals there, exactly the same as this instrument in actual fact. Separate terminals for them. We can plug our thermocouple into there. We just have to make sure we are set up to the right temperature. So we can do this in this screen. We have K-type there that we are set to. We're set to thermocouple, and we've got 20 degrees C for the cold junction temperature there. So that all matches what we've seen on here. Let's go back, and you can see the instrument is actually reading, if I get it in picture there, 108 degrees C against the 109 on our potentiometer, but the only difference is we are actually displaying 3.66 millivolts on this. We do get the millivolts and the temperature together on this. If I wanted to, I could go straight to the millivolts and get that up on the big screen if I desired that. So much quicker and easier to set this up, and obviously we have a significant size differential between these two units, but the result is exactly the same. So what I am just going to do now is flip over to the millivolts on this. I did say that this has a function that you don't find on these modern day units. So to change the dial over to get to millivolts on this, not exactly the flick of a button. Let's get this dial and remove it, and then we get the millivolt dial, and we need to put that into there. Set there. So that's now set up. We are on 3.55 millivolts we had on our MR9270S, and for 110 degrees C we should have 4.509. So procedure is exactly the same again with this. Press the button, you see we get deflection. It's obviously wrong, so we'll dial around. 2, so we've got deflection. Let's go 5, deflects the other way, so we know we're in between. 4.5. Let's go 4 there. Just a little deflection. Very small deflection there. Let's go the other way slightly. See how finicky this is to that's about as close as I can get it with no movement, and that looks like 3.5, 3.6 millivolts, which is obviously not equal to what we were expecting, and that's because I showed in the previous video you don't actually get the true millivolts for the thermocouple in comparison to our tables. You have to take into consideration that this is at ambient temperature, and the millivolts that we get is the differential between hot junction on what we're trying to measure and the ambient temperature seen here. But I did say that this has a function that you don't get on the digital ones. And the keen eyed amongst you may have seen here, we have a cold junction millivolt for. So what I can do, dial this back down to 0, is set this to our millivolt junction. Now we do need the reference table. For 20 degrees C, we are 0.8 millivolts. So we can move that around to there. 0.8 millivolts there, and then we can go again. Our deflection. We knew we were 3.5, 3.6 beforehand, don't we? But you see, we've still got deflection there, so you have to go up. 4, we've got a bit more deflection. Move deflection. A bit more. Or a little bit. There we've got no deflection, and we are 4.4 millivolts against what should be 4.509 millivolts from the table. So by using this function here, I can get a millivolts that actually matches the tables that we download for these thermocouples. Let's say I can't find that function on any of these new digital instruments. You have to do the maths yourself with this. You just get the differential millivolts and you have to manually add on the millivolts for the cold junction temperature. So yeah, surprising, but quite a useful facility if you're working with millivolts for thermocouples. So I thought for showing the sourcing function, we'll use a multimeter. I've got Keysight here set up to measure temperature. We're plugged into our modern digital calibrator. You can see we've just moved the leads over from input to the output. We switch the display over onto output. I can turn the instrument on. The light is on, and you can see this is 0. We're showing 2.3 on our instrument. Interestingly, the instrument is showing 18.6, 18.7 cold junction temperature, whereas this was showing 20, so that's probably accounting for some of the difference. And then whatever temperature we want to do, we just dial in as we go, and our instrument will respond. It's 50 with 47.6. It's got some hundreds. In fact, let's go. What do we need to go beyond? What's this? Let's go. So let's go 750 degrees C, and then that will put us into the second range on our old Thermocouple Potentiometer. But you can see here, 750 degrees C, 30.34 millivolts, 747 degrees C on the instrument. The first thing you'll notice for our sourcing kit, we have no display to say what we're sourcing. So what we have to do is use the measurement side to set our sourcing function here. So we want it to go degrees C, and we will need to change our dial back. Get rid of him. We need range 2 because we're going to go for 750. So, oh, that's iron, don't want that one. Oh, could have been. See, here's your problem, you see. Got to get the right ones. Chromonormal, there's the right ones. A lot easier to make a mess of things with these older instruments. You do have to, and you've got to make sure you put this on the right way around as well. If you put this around 180 degrees out, and it will fit. Just to show you, this will fit that way. And go completely the wrong way, and you will be in an even bigger mess. But we're on there. Set him down to there. There's our 0. We're on 20 degrees C for our cold set, so we'll set that to 20 there. Close him down there. So what we now need to do is dial around to 750 degrees C on our instrument. And we need to join our output to our measurement. We can switch on. And here we go again. Pressing, now we need to put him on to range 2 as well. And then you see we can fly straight over. So now we just dial in. Gone too far. Too far again. That's quite good, isn't it? So now we can use our fine one. Change a bit more perhaps. Yeah, that's not bad there. let's see how we go. We just move straight over to our instrument, and we have put in 754 degrees C we are reading on that. So again, within 4 degrees, not bad, although we were 747 on our digital. We are a little bit out, aren't we? Is that me being half blind? I guess it is moving a little bit, isn't it? $752. Yeah, fairly close. But obviously you have to spend more time really trying to set these up. I'm looking at a funny angle at the instrument, so that's probably accounting for some of the error as well. But we were a little bit closer than we were with our digital. But you take the time with this, you can get perfectly accurate readings with it. It's quite a fun piece of equipment to utilise, and I do enjoy playing around with these. So you do have to think a lot more when you're working with these older instruments than you do take the digitals just for granted, just to set them all up and away you go, whereas these take a little bit more work to do. So what I'm going to do now is clear away, and we'll pop this out of the case and we'll have a look at what's inside. So we have removed our rubber feet from underneath. You can see they're all gone and set over at the side there. And now each of these instruments will just lift clean out. There's our sourcing function here, and then we'll lift out our measurement function, put him over to one side, and there for your enjoyment is lots more cardboard. So we can put him to one side. We'll briefly look at the sourcing function. This is dead easy. Type D battery, and then just 2 rheostats. Your output jack's there, and then our on-off switch. Nothing too major about them. I just noticed that is awfully close to the case there, isn't it? All that bit's plastic. You're all right. Okay, so we are still painted chassis here, but this bit, the battery holder, is actually plastic. Okay, so we put him to one side. So we stripped down our measurement unit a bit more, so you can see here's our dodgy switch. Our output jack's here. There's our rheostat for doing the calibration, and then this here is our main potentiometer with the connections there, and then these are our individual range resistors that you see around here, and the galv button in there, and you can see a bit more on the side there, hopefully. What I did want to show you is how I've dated this unit. So we said about a reference cell that's inside here. Here it is. This is the Western cell. The Western cell is this little chemical monstrosity that produces a very specific output voltage, developed in 1893, and this is actually the international EMF standard from 1911 to 1990. So it has a very, very long history. And this particular one is made by Muirhead. And when Muirhead made these, they usually put the cell type on there, the date and the actual voltage. But unfortunately, that's not on there. All we can see is the serial number, which is 41103. I find it hard to, with the light and everything, I'm not sure how well you can see the serial number on there. But no date, which was a little bit disappointing for me. However, what I do have is another Muirhead reference cell. This is a type D845D, which is the posher version, if you like, of what's installed in this, but it's actually the same cell inside. And when I removed this one and looked at the cell inside, I actually get serial number 41175 and a date of 20th of December 1962. So that is 72 away from this cell here. I don't know what the actual batch numbers were for Muirhead back in the 1960s, but I think you could reasonably assume that they made these in batches of 100. If they did, then that must place this very close to December as well, in which case you'd say this unit was probably built in 1963. If it was the previous batch, so they only did batches of 50, then it might be more towards the beginning of the year, mid-year or something like that. So this instrument then might have come out at the end of 1962, at the very earliest I would have thought, but I'm plumbing for 1963 for this instrument based upon the serial numbers and the dates are on the other reference cell that I've got. So I have just reassembled our little cell here. These cells are quite fragile, both mechanically and electrically, so I don't like having it off its mountings for too long, bouncing around. This, as I said, this is a standard Western cell made by Muirhead. It's a saturated cell and it should put out a voltage of 1.01863. However, to measure these you need a high impedance meter. Even the 10 mega ohms that you have on your modern day DMMs, such as the Keysight here, 10 mega ohm input impedance on DC. If the cell was brand new, you might get away with it, but with an old cell such as this, you probably really don't want to be doing that. The maximum current you should draw should be around about 10 nanoamps to safeguard the Western cell. When you start to draw more than that, the output voltage will drop significantly. Over time it may recover, but you can do permanent damage to them. So really it needs to be measured. I did measure this with my reference kit. Unfortunately that is actually away at this moment in time for calibration and repair in Germany, so I haven't got that. But I will put up a picture of the measurement that I made on this cell when I did have my reference kit, and you'll see it's very, very close to spec. I'm quite happy with that, so loads of life left inside that cell, even though it is from 1962. However, the cell is actually only in circuit when you're doing the standardizing. As soon as you've standardized the instrument and you're happy, then it's just running off the standard U2 battery, or D-type cell, I should say, that we have now. So that's that there. The only other thing to show you on this, which is any real significance, if we pin them over here, hopefully you can see that just here there is a standard probably half watt resistor, I would say that one is, that appears to have been soldered in. I believe that this is a modification. Originally back in 1962 you would have had zinc carbon batteries to power this, and they have a lower output voltage than our modern alkaline cells, so there is a fix to put a little resistor in line. It's actually in line with our calibration potentiometer there, and that will allow for the higher voltages that these kick out and allow you to actually standardise the unit. So I believe that's why they're there. Having said that, it looks to have been done very sympathetically, to be honest. They've even varnished over the connections again, like all the other connections are from the original manufacturer. So yeah, quite impressive really. But that's what it is. I'll try and get it all back together again now. But hope you enjoyed that video. As I said, it's the last one for 2024, so I thought I would do something a little bit different. Thanks very much for everybody who's watched all the videos over the last year and commented and subscribed and liked. It's very much appreciated. Have a good new year, and I will see you again in the next video in January.